last lesson on consolidation, we'll talk about how to compute the rate of consolidation in the field. And what we mean by that really is coming up with a plot of consolidation settlement versus time. So we've already used settlement versus time from the laboratory test to derive the C sub v constant from the test. And the thing is that the lab specimen is very small, right? The thickness is only about 20 millimeters. And the reason we do tests on pretty thin consolidation specimens is that they consolidate fairly quickly. We can do a test with only one load stage per day, typically, so it may only take a week or two to do one consolidation test. Still kind of a long time. Okay, when we go to the field, the layer thickness is much bigger, right? We're not dealing with a 20 millimeter thick layer anymore. It might be many meters, maybe it's a meter, it's going to be thicker than 20 millimeters. So recall our definition of time factor was C sub v, which is a material constant, and then we have time, and we have drainage path length squared. So if we pick a particular time, like let's say that we pick 1 day, for example, if our drainage path length is only 0.02 meters, like for this specimen, the time factor is going to be very high because we're taking a small drainage path length and squaring it, and we get a big time factor. If we go to the field and it's 10 meters thick, now our drainage path length is much longer. We're going to square that number, make it even worse, and our time factor is going to be very small. So what that means is that consolidation really happens much more quickly in the laboratory than it does in the field. And an implication of that is that we can't just take directly the settlement versus time that we get from the laboratory specimen and assume that the field layer is going to follow that same settlement versus time pattern or relationship. Maybe the shape of it will be the same, but the x-axis scale is going to be completely different. And then, of course, the amount of settlement for the field specimen is pretty small too because it's only that thick, whereas the amount of settlement in the field might be much bigger. So the reason we do the lab testing is really just to get C sub v, and then once we have C sub v, we can extrapolate it out to the field. So let's go on to the steps for getting the settlement versus time. The first one is you have to select a representative C sub v value from your laboratory test. And let's go back to the previous lesson briefly and just look at what this looks like. This is C sub v versus log sigma v prime. What we talked about before was that you really have to separate the over-consolidated stages from the normally consolidated stages. That's based on the consideration for whether they were normally consolidated or over-consolidated for that laboratory loading stage. Okay, once we do that, now we can go to the field, and here's our field condition, if we're looking at clay there maybe. What we can decide, is that clay normally consolidated or is it over-consolidated? And based on that decision, now we know which line to look at. We can look at that one if it's normally consolidated, much lower CV, slower consolidation, or we could look at that line if it's over-consolidated, much higher C sub v. Okay, if you don't plot these with different colors or different symbols, you're going to get this mess, and maybe your trend would be like that. You don't really know. So be sure to separate them out into those different lines. And that's the top level consideration. What is the degree of consolidation, over-consolidated or normally consolidated? Okay, so first you look at whether it's NC or OC in the field, and you pick either the blue or red trend line accordingly. After you've done that, there still is a little variation in C sub v versus log sigma v prime, usually these little happy faces. So what you can do is come along the x-axis to some amount of sigma v prime that is going to exist in the field condition, and you're going to start at some value sigma v naught prime and end up at some other value sigma v f prime. So maybe you could take an average somewhere in that region. But anyway, once you know which line to look at, interpolating C sub v from the correct line is pretty easy based on sigma v prime. Okay, then the next step is to compute settlement versus time. And you can do that in a fairly simple Excel table if you want to. The first thing you'll do is get a table of U average and time factor pairs. And these numbers come from Terzagh's one-dimensional consolidation theory. You should be able to One thing, if you do write equations for them, U average must be between 0 and 1. It can never go higher than 1. And then you can compute the time factors, or alternatively, you could put in a vector of time factors and then compute U using U average using the Taylor and Casagrande equations. All right, once we have those numbers, we use them to compute two things. One is the amount of consolidation settlement, and that's really simple. That's just U average times the ultimate amount of consolidation settlement. So before we come in and do this, we have to have done the amount of consolidation already. We have to know how much the total consolidation at time equals infinity is going to be. You know, that's based on like the previous homework assignment. You divide it into sublayers and compute the total settlement. Pretty straightforward. So then you just multiply by this number times that ultimate settlement, and you get a vector of settlements at different average degrees of consolidation. Then you calculate the time. And lowercase t is equal to time factor, which you've already got in this table, times drainage path length squared. And note that that drainage path length is not for the laboratory specimen. It's confusing, I know, because you've got one test that's done in the laboratory, and you have a drainage path length for that field, for that lab specimen. Then you have the field loading condition, and the drainage path length is much longer. So you have two different drainage path lengths to keep in mind here. Be sure to use the one for the field, because otherwise you'll get the wrong times. And then you have C sub V, which you've obtained from your laboratory test. You've obtained a whole bunch of C sub V's and picked the one that's the best representation of your field loading condition. All right, so now we have settlement and we have time. We just have to plot them versus each other. And usually for settlement versus time plots, we plot them descending on the y-axis, because when settlement happens, the ground moves down. So it's kind of intuitive just to plot it this way. I suppose you could plot it this way instead if you wanted to, but you know, usually we plot it down time instead. And what you'll find, if you did this right, is that the settlement versus time plot will asymptotically approach the ultimate settlement as time goes to infinity. This one is time on a linear scale. A lot of the time we put it on a log scale, and then you'll get this kind of double curvature relationship that will still go asymptotic to the ultimate amount of settlement. All right, so what I would recommend is that you could even include these plots in a design report. Say you're doing settlement calculations for a building. You know, you could put that plot in there. You may not be very accurate with it for a reason I'll talk about in just a second. It's really hard for us to accurately compute settlement versus time. Another way of doing it in foundation reports is that we often partition it into the total into the immediate and the consolidation or delayed settlement. So what we might say is that, you know, the settlement is going to be 5 centimeters at the end of construction. That's the immediate settlement, and an additional 5 centimeters over the design life of the structure. Maybe that's 50 years, something like that. Or oftentimes we'll say over 2 years, because oftentimes after a few years there's really not that much more consolidation going on. The reason why this is important is that settlement that happens during construction may not really have that much adverse impact on the structural elements or the architectural finishes of a building, because by the time the building's done being constructed, that settlement's already happened. The consolidation settlement that happens after construction will be felt by the building, can cause cracks and things like that to form. So you want to be clear about that so that you don't get, you know, litigation later if the building does settle slowly over time. All right, now one note that I wanted to point out is that when we go to the field and drill boreholes or push cones into the ground to investigate soil properties, it's really unusual that we find a thick clay layer that's perfectly uniform clay all the way through. What we almost always see is that there are these thin interbedded layers like this one there and that one right there. Sometimes those layers all line up along a particular depth, and it's pretty clear that they're horizontally continuous. And in that case, those drain water away, right? If you load, you know, a portion of the soil, water can flow horizontally through these sand lenses, which have much higher permeability, and get out of the clay. So what that means is that instead of having, you know, if this is double drained, you have sand down here and sand up here. Instead of having our drainage path length be it's now going to be like half this distance between the clay and the sand layer right there, and then you have another drainage boundary happening here where you're going to have that one and that one. So you'd have to solve it as two separate clay layers, and the drainage path lengths are going to be much shorter than if you have the full layer thickness of intact clay. And I drew it this way on purpose, that we don't encounter a sand lens at boring number 2. So what happens a lot of the time is that students might want to connect these layers and say there's a dipping sand layer. Well, that kind of doesn't make sense from a geological perspective. How would that sand get there on that slope? You know, sometimes you can have that if soil is deposited and then subsequently uplifted, you get tilted sedimentary beds, but not typically for young soils. So probably what happened here is that this was an old river channel. The clay was getting deposited, this river was running through and depositing some sand in here, and then it meandered somewhere else and deposited sand somewhere else, and then later in time, as the soil was deposited higher and higher, the river was right here, and it never crossed this line for boring number 2. So when we see a soil profile like this, we really don't know. Is this just an isolated little lens of sand? You know, if it's small relative to the building footprint, it's not really going to drain water away from our site. It won't affect the rate of consolidation. Or is it really continuous? Does this thing continue for a long distance, and is it able to carry water away from the clay and out of the site? If it's an isolated lens, consolidation will take a long time. If it's able to convey water, the drainage path length might be reduced by a factor of 2. And then the time for consolidation is proportional to the square of drainage path length, so it's going to have a factor of 4 impact on time rate of consolidation. So key questions: do those sand lenses drain water, or are they hydraulically isolated, these little patches in there? If they drain water, drainage path length is smaller, potentially much smaller, and consolidation will happen faster than we predict. If we just did boring number 2, we would say the clay layer has that thickness, double drain, so the drainage path length is half of that, but we're going to really over-predict the amount of time it takes for consolidation to happen. Also, are there other sand lenses that we don't know about? Right? We don't go and drill everywhere in the site. We drill a few boreholes. There might be things that we missed. So there might be some sand lenses in there we don't know about. Maybe we would put a boring here and then one over here, and we would miss all those sand lenses and wouldn't even know they're there. So the result of all of this is that consolidation usually happens quite a bit faster in the field than what we predict, based on our knowledge of drainage path lengths and our best guess of what they are. So an outcome of that, let's say that you predict it's going to take 500 years for a layer to reach 95% average degree of consolidation, and then you say, oh, well, the design life of the structure is only 50 years, so only a small amount of the consolidation settlement is going to happen during the design life of the structure, so we don't really have to worry about it. Well, that would be a big mistake, because probably the clay is going to settle faster than you think it's going to, and you don't want to rely on this delayed consolidation to kind of save your structure. It's important to get an accurate estimate of settlement rate, but don't rely on it to provide safety for your structure, because that would open you up to liability and potential for lawsuits later on. So just be conservative. You know, generally we don't provide the settlement versus time curve. We just say this much will happen immediately, this much will happen after construction, and that's a safer way to do our recommendations.